So as we move into this first module, there'll be the introduction to stack effect. And what most people are aware of is in cold climates, so the building is warmer than outside, air comes in at the bottom of the building and then rises within the vertical shafts and leaves at the top. Some people believe that stack effect exists because hot air rises, and that's actually not true. Hot air does rise, I'm not denying that, but the reason why stack effect gets set up is because the air inside the building is lighter than the air outside the building. So the column of air inside the building weighs less. And I'll come back to that in a few moments with an example. But this buoyancy force is generated by the indoor-outdoor temperature difference. The image that you see here is for winter mode. In summer mode, where the outside is warmer than the inside, the air inside the building is heavier, and so air will tend to come in at the top and leave at the bottom. When we talk about stack effect, though, it's not all bad. There are many, many benefits to stack effect, and one of the sort of most obvious ones that people are most familiar with is natural ventilation. And this is true in all climate types, and for the example that I've got here is effectively showing that in 15 degrees Celsius, 60 degree Fahrenheit conditions, air comes in at the bottom of the building and leaves at the top. This is the way a chimney might work on a fireplace. And the stack effect in this particular case is gentle enough that it's allowing air movement or generating air movement, but not causing other undue problems. So when we talk about stack effect, there's sort of two aspects to it. One is the driving force, and then there's the issues and consequences. And when people with a building discussing stack effect, what they'll sometimes do is they'll ask the question, how can I get rid of stack effect in my building? That's the question that's asked often, and whereas the right question or better question is, how can I reduce the severity or the frequency of a stack effect to make it so that it doesn't become a problem in my building? That's a better question to ask, because the presence of a building and the presence of a temperature difference will result in stack effect. So let's talk first about a case study. This is a building in Denver, Colorado. I've actually grabbed a YouTube video to allow you to see the influence of stack effect. The building is 44 stories, approximately 166 meters, 550 feet. The outside temperature is 10 Fahrenheit. The indoor temperature is 70 Fahrenheit. It's not what we would call a tall building. It's moderately tall. And this is not a severely cold winter. I realize for some this is cold, but it's not severe in North American and European standards. And this is a good way of showing what ends up happening. So this video starts with the introduction by the fire chief.
Hello, I'm District Chief Dave McGrail with the Denver Fire Department. I'm here with members of Engine Company 1 today. This is firefighter Ken Ingley, and this is firefighter Jesse Weed. We're here at a 44-story commercial high-rise building in downtown Denver, and we just wanted to use a kind of a crude method to illustrate stack effect in this building. It's a very cold day today in Denver. It's about 10 degrees outside, and the ambient temperature inside the building is about 70 degrees, making for a 60-degree temperature differential, which would contribute to a very powerful stack effect on this cold winter day. So I'll have firefighter Jesse Weed open the door, and firefighter Ken Ingley is going to use this stick that we have streamers on to illustrate the powerful stack effect in this building today. So it's when you come into a building and you're using one of the standard doors on either side, typically of a revolving door, and you realize it's very difficult to open it up, that's just a positive stack effect, which is going to be very powerful on a cold winter day like it is here today. Thank you.
So as the fire chief noted, this air movement is driven exclusively by stack effect. And one of the things I wanted to do in this screen cap that I grabbed is to just note that the kind of door that firefighter is moving is actually what we refer to as a pressure balance door. The door is not pivoted at the edge. It is pivoted somewhere towards the center of the door, which then means that there's pressure acting on both sides of that pivot, which helps to relieve the force the opening force that's actually required to move it. I'll come back to that in a little bit because it plays a role in what we talk about in terms of the criteria. So when we talk about potential stack effect impacts, there's a variety of them, and I've got a short list here of things that you've probably experienced yourself. And one of them is whistling airflow through doors and cracks. And in that particular case, the door could be an elevator door, it could be just a unit door to apartment. And whistling itself is a complex issue that's driven by not only the shape of the crack, but also the spacing of the crack or the configuration, how far apart are the two surfaces that are causing the whistling. And there's different types of whistling. The flow rate through the crack can set the tone, and that sound can range from something like a whistle to a hum. And I've even recently in a building tour heard of a flapping noise where a piece of rubber was flapping backwards and forwards and creating a rather unusual sound. So that kind of auditory noise can either be something that's benign or it can be a problem. And in some cases, the whistling noises in an apartment building can actually cause problems for people to sleep. Another potential problem is opening and closing doors. And this can be both a nuisance and a safety issue. And so, for example, if you're in an apartment building and you're trying to get out of your apartment, but you've got outside windows open, the pressure stack effect force can actually cause difficulty opening your door. And here, a choice of the door openers and closers is important to make sure the building is accessible and safe. We don't want the doors closing too quickly and slamming, but we also want them to actually close in a positive manner and close and seal so that they help control stack effect. Another challenge that we've seen in some buildings is the difficulty controlling temperatures where there's excessive infiltration on some floors. So for example, a space could become too cold, such as the lobby to a residence in a cold climate. The stack effect is driving cold air into the space. Another example is in the upper part of a building, it can get too hot in a hot climate. And an example I'll give to you is I was at the top of a tall building in Dubai. There was a gymnasium up there as well as a pool deck. And as people were going out to the pool deck, there was a surge of warm air that was coming in, raising the temperature inside the gymnasium, which then made it difficult for the athletes to exercise. And by the time the air conditioning system had caught up and made it cool again, someone else came in or out of that pool deck. So there's an example where that can affect building occupants directly. Another example of problems we see is with elevator door operability. And what we mean by that is an elevator door starts to close and it's not able to close completely. It's difficult to define where that happens. It's intermittent, and different elevator door manufacturers have different mitigation strategies. So for example, some might adjust the force of the closer, some might adjust the seals around the elevators to relieve the pressure. So there's a variety of things there, and I'll show you a picture of an example of that failure later on. And then finally, another one is increased building energy costs due to uncontrolled airflow from outside. So as you can imagine, if we've got a building and we're warming it in the winter, having uncontrolled air come in the bottom of the building can cause an unmanaged energy loss associated with heating that air that's come in. At the moment, it's not clear how much energy is actually lost via stack effect, and that's actually a piece of research that we have underway at our office, is to evaluate that more completely. So let's talk a little bit about how stack effect gets set up. And earlier on I said that stack effect is not caused because hot air rises. What happens with stack effect is it's a pressure issue, and it's a differential pressure that's caused by different weights of air inside and outside the building being a different weight. And so I'm going to draw your sort of attention to this extreme example where I have a tube of water on the left and a tube of air on the right, and they're unconnected. And then what happens is when I connect them, you know, of course, intuitively that the air will go up into the top of the tube of water, and the tube of water will drop down and sink into the tube of air. And so what I'll have effectively is so the bottom of the two tubes is water and the top of the two tubes is air. Now that's not the way it works in a building. What ends up happening in a building is if you now imagine that tube of water is actually the outside conditions on a cold day. The outside air is warmer than the inside air, so it weighs more. The inside, the tube of air, is lighter, and what happens in this particular case is the flow is still set up where the air wants to rise up and leave at the top of the building, and this water, or also that cold air, wants to drop and flow into the bottom of the building. But if I have some magic where I'm able to turn the water at the bottom of the building instantly into air, and at the top of the building I'm able to instantly turn that air into water as it leaves the building, what effectively happens is we've set up stack effect in a building. The way a building works is as soon as the warm air from inside the building leaves the building at the top, it's instantly made cold by the enormous volume of air that's outside. At the bottom of the building, when the water comes in or that cold air comes in, the building HVAC systems warm up that cold air and turn it into warm air. So now all of a sudden it's warmer than outside. So this process of this water or cold air being turned into air or the inside of a building sets up the stack effect, and that's how buildings behave. So in this description, at no point have I said hot air rises. What I've said is it's about a pressure difference between the two. Let's talk about a specific example. And here I've got a building that's approximately 1,300 feet tall, 400 meters. And the inside and outside conditions are listed on the page, and it's sort of 21 degrees Celsius inside and minus 17 degrees Celsius outside. And when you do the mathematics, and the mathematics is on the right-hand side of the page, what we end up getting is a 700 Pascal pressure difference. And that 700 Pascal pressure difference is divided up and down the top of the building. In this case, I've coarsely or approximated it and said that the neutral plane is about halfway up. So that means that 350 pascals at the top and 350 pascals at the bottom. This is an example for winter where I've got air that wants to come in at the bottom and I've got air that wants to leave at the top. When I set up a summer scenario, the temperature difference is a lot less. And in this particular case, I've said it's approximately 21 degrees Celsius inside and 35 degrees outside. That temperature difference is a lot less. And as a result, the stack effect driving force is also a lot less. In this case, it's 200 pascals. And as the image shows, I've sort of split that approximately 50-50 between the top of the building and the bottom of the building. And this is an example where we start to see that in summer or warm climates, stack effect is not going to be as strong as in cold climates, and that's simply because the temperature difference is not as great. That said, summer stack effect can also be more difficult to control than winter stack effect, and I'll talk about that in a couple of minutes as well. When we take that 350 Pascal winter pressure difference and we spread it across the building, what ends up happening is we have the 350 that wants to come in at the bottom and the 350 that wants to leave at the top. And on the image on the right, I've just tried to plot that and show that it's essentially a straight line between that plus 350 at the top and the minus 350 at the bottom. And at some point in the middle, there'll be a neutral plane, and we'll talk about the neutral plane in a couple of minutes. But that's the way the pressure's laid out across the building. Now, when we start looking at what the consequences of that magnitude of pressure is, this is a useful image in that this tennis dome is under approximately 250 to 750 pascals. And so to put that into IP units, that's 1 to 3 inches of water. And what this ultimately means is that the weight of that dome is being kept up by the pressure of the air that's being pushed into it. When you look at the kind of door that tennis dome has, it includes a vestibule on the left with a motorized door and good solid closers. Or on the right-hand side, in the same image, you can see that there's a rotating door that will have very, very good seals and brush connectors that go right to the shroud of the rotating door itself. The photograph on the right is showing a set of frameless glass doors in a residential building. This is a building that we've seen. And this is the equivalent that sometimes is designed into a building to control the same pressure. And clearly, the control of 350 pascals for a tennis dome on the left-hand side is well done. It's managed properly, but it's not what you would call particularly transparent. It's not architecturally pleasing. The picture on the right is an architectural version of trying to control pressure, but it just won't handle the pressures. The doors will be difficult to open, there'll be lots of whistling, and it'll likely transport some of the stack effect problems into the center of the building.
Coming up in Module 2, criteria for the assessment of problematic conditions.